Hello and welcome to Week 9, Lecture 2 of CO 442642 Graph Theory. Today we'll be discussing Ramsey's Theorem. So what is Ramsey's Theorem? Well, before we get to Ramsey's Theorem, let me discuss Ramsey theory. So here's just a general philosophical question. Can we find order in chaos? So if we're given chaos, is it possible to find order? Or say that differently, can we find structure where there is none? So if there's no structure, is there always some substructure? Is there always structure even though you think there isn't any? And this might seem weird and you might say obviously not true, but really it is, and that's the point of Ramsey theory. So let me make this a little bit more mathematical and graph theory wise, to say what substructures are necessarily present in large enough graphs. So again, this is a natural question harking back to various questions we've seen in extremal graph theory, but maybe let me make it a bit more concrete to say, does every large enough graph contain a large clique or large independent set? So you have a large clique or a large independent set. And so that's kind of a natural question, right? So I want a larger clique or independent set. If my graph is large enough, will it contain one of those, right? I mean, I need to have both cases because I could just be a clique or an independent set, but somehow is that structure? So that's what we're suggesting when we say, structure where there's none. So you could just kind of have a random graph, but is it always possible to find some subpart that has structure? So here, all complete or all anti-complete, all adjacent or all non-adjacent would be the structure that we're looking for. And it turns out this question and related questions form a branch of graph theory with its own distinctive flavor. That's called Ramsey theory, after Ramsey and Ramsey's theorem, which we'll be discussing today, which answers this question. So it has a slightly different flavor than extremal graph theory, where maybe we're interested in maximizing or minimizing subject to constraints. Here we're given something and we want to find order among it. We want to find certain substructures, assuming you're large enough. And they go somewhat hand in hand and are clearly somewhat related, but maybe distinctive enough to have been named its own subfield. So what is Ramsey's theorem? It's saying the answer to these questions, the more specific ones, is yes. So if Ramsey proved in 1930 that for every positive integer r, there exists a number n, such that every graph G with at least n vertices contains either a kr, that's a clique, or a kr complement, which is an independent set, but as an induced subgraph. And so induced there just to make sure that you can't cheat with the independent set. So you can really find a large clique or a large independent set. So that's what we'll be trying to prove today. We'll be giving various proofs of that. I'll just say, though, this goes to a more general theory that therefore Ramsey started, called Ramsey numbers. Just as we have Tarot numbers, we have Ramsey numbers. So the Ramsey number of a graph H, denoted R of H, is the minimum integer n, such that every two coloring of the edges of Kn contains a monochromatic copy of H. So this is a different way to think about the problem. Instead of finding a clique or an anti-clique, you could kind of find H or an anti-H. So maybe it's better to think not of graphs at all, but of two colorings of the edges. You want to find, say, a red H or a blue H. And Ramsey's theorem is thus equivalent to the statement that R of kr exists for all R, that the Ramsey number of cliques exist. That they're actually it is well defined. There is some, number, right? All right, so that's the Ramsey number for n and h. And then why is this? So, so we have this Ramsey number that for h, there is an n that exists, but why? Maybe pause a moment and think. Why, are these equivalent? Maybe it's very clear to you, just again processing. It's this edge, the coloring of edges is related, namely that if we color the edges of the graph red and the non-edges blue, we get a coloring of the complete graph. So that's the relation. So in the statement as of Ramsey's, we have kind of a graph. How is that related to Kn? we color the edges of the graph red, so with one color, and the non-edges become the second color, blue. And then finding a monochromatic H, so if you find a red H, that's finding the clique Kr. If you find a blue H, that's finding the anti-clique Kr complement as an induced subgraph. And these are also vice versa, right? So if I have some two coloring, then I can turn that back into a graph by turning, red into edges and blue into non-edges. So it depends which way you want to think about it. It's going to be more helpful, maybe for future generalizations, to think of it in the coloring context. And that's how most Ramsey theorists think of it, as kind of an edge coloring type of problem. But again, it's a different flavor than visings or things. It's more having this kind of structural, has a little bit more of an extremal flavor than a structural flavor. All right, so there's that. And I'll also point out then it follows that R of H exists for all H, right? Why is that? Because, if you can find a monochromatic clique, then, KVH, then of course you can find a monochromatic H. And then you're done there. So, this implies, Ramsey's theorem implies the existence for monochromatic cliques and therefore monochromatic any subgraphs. So there always exists this number which you can force. So that's structure from chaos, order from disorder. That eventually, if we're large enough, we can find a monochromatic copy of any H. So we're going to prove this today. So I'll give you, there's a couple of, different proofs, but they're all somewhat similar. So we'll do one, which is quite nice, and then we'll talk about generalizations and prove those, which are, kind of in a sense give a different proof, but really you'll see the way I'll do it will be the same. Okay, so proof of Ramsey's theorem. Well, for r equals 1 is trivial, right? I mean, there's no edges to worry about. Right? Finding a k1 or k1, you're going to find a vertex, that's fine. So we can assume r is at least 2. And now what do we do? Here's the key. We'll let n be 2 to the 2r minus 3. So some exponential in r, and it turns out, as we'll talk next week when we talk through bounds on Ramsey numbers, that exponential is needed here. And this is pretty close to the best upper bounds, so we'll discuss that later. But let n be 2 to the 2r minus 3. And then here's our nice claim. So claim that for every I in 2r minus 2, there exists a vi, subset of the v of g, and a little vi in big Vi. So you can find a vertex in this set with the following amazing properties. That vi is of size 2 to the 2r minus 2 minus I, right? So that you're some kind of power of 2. It's going to be decreasing as I is increasing, so halving each time. We're going to find the vi to be a subset of vi minus 1 less little vi minus 1 for all, of course, larger I. So we're going to kind of remove the little v's and then find a subset among what remains in such a way that the little vi minus 1 will be either adjacent to all the vertices in big Vi or to no vertex in big Vi. So kind of all or nothing principle, that you're adjacent to all or non-adjacent. And that's, of course, going to be helpful for finding cliques or anti-cliques. So this is the claim that we can repeatedly, you can kind of see maybe it's algorithmic for how it was created, like that can repeatedly extract these VIs, little VIs and big VIs, and with this property that their sizes are decreasing by half, and then that you get this all or nothing property. So proof of the claim, well, we go by induction on I. So for I equals 1, that's not very hard. We can just pick an arbitrary subset of size 2 to the 2r minus 3, since we have at least 2 to the 2r minus 3 vertices, and pick a vertex v1 arbitrarily. So then condition 1 is satisfied and 2 and 3 are trivial because they don't apply clearly for I is at least 2. They only apply for I at least 2, so not for when I is 1. All right, so then that's fine. Now we go to I is at least 2. I will note that vi minus 1 less little vi minus 1 is 2 to the 2r minus 1 minus I minus 1. And this number is odd, you should realize. So it's 1 less than that power of 2. And now we have to find a vi among this, right? So we delete the little v. We have to find the big vi among these vertices with the property that you have the right size and this all or nothing type thing. And you could think about this for a little while, but you'll convince yourself you can do this, right? Why? Well, either VI is adjacent to kind of at least half of those vertices, or it's non-adjacent to at least half. And so if you think about what that means with the power of 2 and it being odd, either you're adjacent to 2 to the 2 minus 2 to the 2r minus 2 minus I vertices in the set, or you're non-adjacent to that number, right, which is the half rounded up. And so then we can just let that set, it's not, and either the neighbors or the non-neighbors, we take to be the new set VI. So I didn't kind of write that there, but that's what you would do, and then you're done. So really you're done with the proof of the claim at that point. So either you always take kind of the neighbors or the non-neighbors as you're picking it, whichever one is larger. So majority kind of rule. Whichever one larger, and you keep extracting sets in this way. So that's our claim. What does it mean? Well, here's a picture, right? So say you take V1 and say you take that it has more neighbors than non-neighbors. So then we let V2 be its neighbors. Then we pick, like V2 and we say, oh, it has more non-neighbors. You pick that. Then you look at V3, you pick a little V3 in there. Again, let's say majority non-neighbors. You keep doing that. And the point is, because of the sizes, this process continues. We don't run out of vertices. At least for the 2r minus 2, steps. And now why are we done? So maybe you could stare at this picture and think, do you see a large clique or anti-clique in here? So, well, among the 2r minus 3 vertices, so v1 up to v2r minus 3, the point is that at least r minus 1 of them satisfy condition 3 in the same way, right? So v1, in our picture is doing the neighbors, v2 is non-neighbors, v3 is non-neighbors, v4 is neighbors, etc. R minus 1 of them, the majority of them, will all act in the same way. So R minus 1 of them will either be neighbors going forward, or will have non-neighbors going forward into the larger VIs. So why is that enough? Well, so that a different way to say that is there exists an I, right, in subset of 2r minus 3, such that for every I and I, either VI is non-adjacent to VI plus 1, or VI is adjacent to all of VI plus 1, with the additional condition, sorry, I left that out, that I should be size R minus 1. And then at that point, you can take those VIs and the last one, the V2R minus 2, which I didn't mention above, but you could take that one and they would induce a KR or anti-clique, the KR complement in G as desired. So these are minus 1 plus that last vertex. By the conditions, they'll either all be adjacent or all be non-adjacent, and we'll be done. So that concludes the proof, our first proof of Ramsey's theorem. It's kind of nice. You just pick out, you majority rules, and eventually, if you're willing to half and so on, get to finding a clique or anti-clique. Okay, so that was our first proof of Ramsey's theorem. I wanted to talk about generalizations of Ramsey's theorem. So what's the first generalization you might consider comes from the coloring perspective, right? Here I was talking red and blue, edge and non-edge. So the edge and non-edge, you don't really see it, but if you think about red and blue, there's a clear generalization is why two colors? Why not use C colors? Why not red, blue, and green, and so on? So we can first ask, if I have a coloring of the edges of Kn with C colors, is there always large, a monochromatic clique there? So that's one generalization. There's a second generalization, maybe less obvious to you, is hypergraphs instead of graphs. So instead of having edges, pairs, what if I kind of are coloring the triples of, all the triangles inside of Kn? And then I want to kind of find a subset where all the triangles are the same color, a large one. So that would kind of be the generalization there. So let's make this a little bit more formal. Let's say let X be a set. We let X, brackets to the K, we've used this before, denote the set of all K subsets of X. So that's more in the hypergraph language, right? X1 would just kind of like be the vertices of the set. X squared would be the pairs, i.e. like the edges of the set. But more generally, we could think of all the kind of the K subsets, these hypergraph type edges. And then we can define what it means to be monochromatic. So given a C coloring of the K subsets, so we color each, triangle or K4 or whatever with colors, then we say that a subset y of x is monochromatic if all the elements of y to the k have the same color in that coloring. And so this is, would just be like Ramsey if c was 2 and k was 2, but here we're generalizing. And now the theorem is that this generalization holds, that for every k, c, and r, there exists an n at least k such that every n set x and c coloring of x to the k has a monochromatic R subset. Right? So Ramsey said whenever we two-colored, the edges of kn, then we found a monochromatic kr. Now we're doing it more that we're actually c-coloring, so c colors these k subset x to the k, and still we can find monochromatic subsets. That there is some n for every such, k, c, and r. So that's kind of our, hypergraph multicolor Ramsey theorem, and we'll prove that. Now you could do it basically as I laid out in the first proof we had of Ramsey's theorem. So you could do it, it'd just be a bit tedious, right? Because how do you choose the vertices? How do you go about doing that argument? And you could try to work out bounds as well, but it gets trickier. So instead of that, we'll do another nice, very cool proof, which is to pass to a third generalization. So we'll derive this theorem from a third generalization, which is the infinite version. So we're going to prove that actually this holds for infinite sets, for infinite graphs, and then we're going to derive the finite version from the infinite. And that's very nice. So it's kind of not having to worry about, any bounds, not really having to worry about, which n is going to actually make it work. So you'll see how this will work. But let's talk about the infinite version first. So infinite Ramsey. So actually, Ramsey's theorem holds, for infinite graphs, and actually even this multicolor hypergraph version. How does that work? Well, let k, c be positive integers, and x an infinite set. Then we claim that every c coloring of x to the k contains an infinite monochromatic set. So maybe stop and just appreciate that. So, if we c color the k subsets of an infinite set, there's an infinite monochromatic subset, right? Our definition of monochromatic applies also to infinite. You can go check that. But we can actually find this. So I think that's quite nice because, right, remember what the idea of Ramsey's theorem, order, from chaos, right? That you can find this kind of big monochromatic, clique among, if your graph is large enough. What's a nice way to do that is make big infinite. So, given infinite, we can find a large one, i.e. also an infinite monochromatic subset. So that's quite nice. All right, so now we're going to proceed with the proof of infinite Ramsey. How do we do that? Well, we'll go by induction on k with c being fixed. So you fix the number of colors, they won't be so important, but then think about doing induction on k. And we've kind of already, well, we didn't do it in the infinite case, but we kind of addressed k's too for finite Ramsey. But let's actually back up. What about for k equal 1? That's even more true. So for k equal 1, what is it? You're just taking a c coloring of kind of the vertices of x, of the actual elements. And if they're infinite, certainly pigeonhole, there is one that's infinite. So that's going to be true. So we assume that k is at least 2. And now we continue. How do we continue? Well, we continue much like we would in the Ramsey theorem. We're going to have a claim. So instead of these sets vi, I'll call them xi, because we have a set x now. So for every I, 0, 1, off to infinity. So now we're not going to stop, right? We're going infinite. There exists an xi, a subset of x, and a little xi in the big xi, such that the same kind of things hold. 1, instead of worrying about the size, we'll just require that the xi's are infinite. 2, again, that xi plus 1 is a subset of big xi minus little xi, that you're always contained, they're kind of telescoping, removing the little xi's. And that all the k sets xi union z, where z is in xi plus 1 to the k minus 1. So if you take a k minus 1 subset of the part that, the next set, and add xi to it, they claim as they have the same color, which we'll call this associated with that color with xi. So this should remind you of exactly our finite, first Ramsey proof, where we took these vi's, right, and we kind of did all edges or all non-edges, so which in color terms would be all red or all blue. So that's kind of what we're doing here, but now in a hypergraph way. So instead of just thinking about edges, they might be hyperedges. So we kind of want it to find a subset, where all the hyperedges from xi into that set all have the same color. And so how do we do this? Well, it's basically the same, except we have to think about having multiple colors, and we have to think about this k thing. So here's the proof. So again, you kind of go by induction on I to build up this set. So just as before, when I is 0, you can just let x0 be x, the whole set, that's infinite, and pick an x0 and x0 arbitrarily, you'll satisfy 2 and 3. So just as before, just start arbitrarily, that's fine. And then you assume I is at least 1, and now the key is, how do we find this, monochromatic set? So before we kind of took the majority one, when it was red and blue. If there were multiple colors and k is 2, you could still take the plurality one, the one with most. Here, though, we'll instead kind of use induction. So how to get to work with hypergraphs? Well, we construct a C coloring of xi minus little xi of the k minus 1 subsets thereof by letting the color of a k minus 1 subset be the same as its color you had when you added in xi. So kind of you can project the colors down you can project out xi and get coloring of these z's. And then what do? We know by induction on k, xi minus little xi is an infinite set. We have a C coloring of its k minus 1 subsets. So by induction on k, there exists an infinite monochromatic subset xi plus 1 of this coloring as desired. And then that's the one you want, right? Because then all of the, it'll be monochromatic there, so xi will all be the same. The sets xi, z will all be the same to that subset, and it's infinite as we wanted. And clearly a subset of xi minus little xi. So that's kind of the nice trick. You use the induction on k, right, and that you can do the infinite. Okay, so that's our proof of a claim. We're almost done. Again, we have to finish the infinite version. We do that in the same way as before, but now in the infinite case. So what's the point is, we associated each of these. So that's exactly like what we did before when we had the v's, right? V1 was all neighbor, V2 was non-neighbor, V3 was non-neighbor, V4 was all neighbor. So here we're doing that, but again with multiple colors. But since C is finite, one of the C colors is associated with infinitely many xi, right? So one of the C will appear, before we just kind of said, when do we have enough reds or enough blues, enough neighbors, enough non-neighbors? Now here we have to go infinite. So we're going to just say, oh, they're finite, so one of them is associated infinitely often. And then those xi form an infinite monochromatic subset of x as desired. And then we're done, right? Because each of them telescopes forward the same color, and so you can see that's an infinite monochromatic subset of x. Okay, so that's the proof of infinite Ramseys, a lot like the finite one we did, but we dealt with the hypergraph issue, these k's, we dealt with the multiple c's, but it is quite nice. Now, where do we go from there? Well, now we're going to derive the finite version from the infinite version by a process that's generally referred to as kind of compactification or bicompactness. So how does this work? Let me remind you what the finite version was. For every k, c, and r, at least one, there is an n such that every n set x in C coloring of xk has a monochromatic R subset, right? So here, we now, x, instead of being infinite, we have kind of R is finite, we still have k and c, and we need to show there's an n large enough. And the point is, you can really derive this mathematically from the infinite version. So somehow, because of the nature of what it means to find a finite monochromatic set, you can really do this. So this will be a type of argument generally called compactification or bicompactness, when you can derive a finite theorem from its infinite theorem, from its infinite version. You can't always do that, but as you'll see at the last step, we can do this because of the nature of what it means that it's a finite thing to find a finite R subset that's monochromatic. So let's begin this. How do we do it? We suppose not, right? So that is, the statement fails for some k, c, and r. So you tell me, it fails for some case C, and we can't find an R. And what does that mean? That for every n, at least k, there is a C coloring of the k subsets of n with no monochromatic R subset. Right? So somehow the idea is we failed, right, for every n, there's always this kind of bad coloring of the subsets with no monochromatic R subset. So we'll call such colorings bad. And now intuitively, that you should kind of realize, somehow we failed, for this K and C and R, always we're always finding bad colorings, then intuitively this must contradict the infinite version, right? So you're saying we can never find a finite, an R subset, but yet the infinite one promised an infinite monochromatic subset. So something must be going wrong here. Now that intuition can lead you astray in general, but that is what we'll do to work out. So we'll derive a contradiction by showing that there is a bad coloring of the infinite set. To that end, we'll let Vn be the set of all bad colorings of n to the k. Right? So we're claiming exactly in the line before that, for every n there is a bad coloring. And if you think about it though, if you're an element of Vn, call it little g, so if you're bad coloring, then if you restrict that to n minus 1k, so if you throw out that last vertex, the vertex n, then you're still bad, right? You still don't have a monochromatic, R subset, right? If you didn't have it in these, throwing out some vertices, you still won't have it. So we'll let F denote the restriction when you throw out that last element. And then what's the point? Well, again, similar claim, but kind of in reverse now. So now we want to construct a bad coloring of the whole set. So I claim that there exists gk plus 1, off to infinity, so that gn is in Vn, that it's bad, and that the restriction f of gn is equal to gn minus 1. So kind of we're going to create a nested sequence of bad coloring. So we're going to have a bad coloring of gk, of the first k vertices. We're going to extend that to a bad coloring of k plus 1, and so on, off to infinity. And then the idea is kind of by compactness that will form a nice coloring, a coloring of the whole set, the whole infinite set, which will be bad, a contradiction. So how do we prove this? Well, I'll do exactly what I just said. I'll prove the stronger assumption that Gn extends to infinitely many elements of the VI. Right, so we want it to extend, so we'll just require, when we're doing this, to make sure that we don't run out, that you always extend to infinitely many elements. And how do you do this? You do it by induction on n. So for n equals k, this is obviously trivial. And if you go to n, bigger, strictly greater than k, since gn minus 1 extends to infinitely many elements, then there is some extension to the next vertex with restriction where f of gn is gn minus 1 that extends to infinitely many. So this is the part you have to think about, but right, so if I have a bad coloring of n minus 1 vertices, I know it extends to infinitely many bad colorings, then what happens? Well, there's only, so many extensions to the next there's a finite number to the next vertex n. When I add an n, I have to think about how the k sets could be colored that include n, but there are a finite number of them, so there are only finitely many extensions. Well, think about the properties with restrictions, right? So, infinite, I can get somehow to larger ones infinitely often. Well, then there must be one of those that also extends to infinitely many bad colorings, and then that's the one we want. And now you just take it all together. You can define a C coloring of all of the vertices 0, 1 up to infinity of all its k-steps by letting the color of a set be the color that all of these agree on, right? So they always, the idea is they always extend, they always agree, so we're really building up a coloring. So, every, subset y, every k subset y will always be present at some finite point, right? So then at that point, whenever we discover all of its vertices, we're going to give it a color. It's going to stay that color forever, so we give it that color. So we let g of y be g of max y of y, coming from this function, the gn's. And now the claim is that g is a bad coloring contradicting infinite Ramsey, right? So we've actually kind of, used these finite bad colorings and kind of took an infinite increasing subsequence in the right way to build this kind of infinite bad coloring. But that's not possible because of infinite Ramsey says there's no bad colorings of an infinite set, right? And so let's just think about why that is. So do you see why it's a bad coloring? Why there's no kind of infinite monochromatic subset? Well, really there's no monochromatic R set, right? Really bad coloring as we've defined it. And it's because of this finite nature that I alluded to before. That if you had an R set S, right, and you wanted it to be monochromatic, that's impossible. Because the R set S is contained in kind of the vertices up to its maximum, right? It's finite. So at some point we discovered it, and we colored in a way that it wasn't monochromatic, right? So, because of the nature that a bad coloring has a finite, witness, a finite description, has that's kind of the idea, that each of these sets is finite. So like if you actually found a monochromatic, set, it would be finite, you would have discovered it somewhere. So that doesn't happen. We always avoid it. And that's generally the idea of what we mean by compactness. You can go, look this up, check Wikipedia, but coming from kind of topology and logic and arguments about that, but this is a more often general principle that you can take things in infinite theorems and convert them to finite. Or vice versa, that if you can prove things for every finite number, then you can actually translate that into proofs of the infinite. So they kind of go between that, they are related, assuming the qualities of the properties you're looking at. This kind of, that you somehow would detect them in the finite case. That somehow, for the infinite, if it was to go wrong, it has to go wrong finitely. So that's kind of the idea. So those are two proofs of Ramsey's theorem. You could argue they're really the same proof, but we proved the generalizations to multicolor, to hypergraphs, which are very nice, and also to infinite, which is also quite nice and easy to remember. But hopefully that first proof, you can remember it. Really majority proof, this kind of all neighbor, all non-neighbor, that's how you go about doing it. We'll tune in next week when we'll talk more about Ramsey numbers. So what bounds can we actually get? We've kind of seen an upper bound that's not too bad. We'll talk about lower bounds. We'll talk maybe about some of the specific numbers, but just this general theory of Ramsey, finding order in chaos, finding structure where there is none. So until next time, see you then.